Hi everybody, my name is Rajesh Kaveti. This presentation goes over HBASE in particular and explains the concept of columnar database. We will walk through the installation of HBASE along with an overview of CRUD, which is the create, read, update and delete operations on HBASE using Java. And then we'll wrap up with some of the concepts of HBASE. So at a high level, HBASE is an open source, distributed, sparse, and column-oriented store modeled after Google's Big Table. To drill down more into this definition, distributed means that it basically runs on low-cost commodity servers. Sparse means that any row in the data store would not have or does not have to have a strict schema, so one can add columns to a row in a way one would do it, let's say, in a map. Column oriented facilitates some control on how data is stored on the disk. So the advantage is that if you know that one of the columns will not be stored with another column, so then it can be stored in separate files. So that kind of gives you more efficiency. It is indexed by row key, column key, and timestamp, and we'll talk about these coordinates as we go forward. It is designed to run on a cluster of computers, and it can be built on commodity hardware, as I talked about. So what are the usage scenarios for HBASE? HBASE is good for scenarios where there is data running in hundreds of gigabytes or up to petabytes. It is good for cases where one needs very high write throughputs. And given its distributed nature, one of the good side effects is that it has a very high in-memory cache capacity. In a traditional database, if you want the same kind of caching capabilities for a cluster which, let's say, has 100 nodes in it, you would have to have a significantly big database node, which would be fairly expensive. Moreover, just to load the cache, it would take you some days. So that way it does give you a very good in-memory caching capability. The last one is the data layout. It is very efficient in terms of key lookups. One of the compelling parts of HBASE is that it is cost transparent, and what that means is that you exactly would know how many data seeks you will have when you want to read something. In a traditional database, that is something that you do not know. There is no penalty for sparse column. So if you have data with STRUMI, which is not structured, it's kind of a semi-structured, then you can also use this, and HBASE provides a very efficient model around that. HBASE is a column oriented, and we'll talk more about that. All relational databases are row oriented, moreover, as far as the transaction goes, HBASE has limited transaction capability, and it does guarantee only at the row level. You can increase throughput easily in HBASE by adding more nodes. The support for query language is very limited. There are 5 basic commands for interacting with data in HBASE. That's get, put, delete, scan, and increment. The only way to query HBASE based on non-row key value is by using filtered scan, and we can talk more about that. So this is the overall architecture, and before we get into the installation of HBASE, I just wanted to kind of give you an overview of how HBASE looks like. The components that we see here are master server, region servers, HDFS, and Zookeeper. HBASE uses HDFS as its reliable storage layer. It handles the checksums and replications and failover. You can use any file system, even local file system for that matter, but obviously it's not recommended. All the good features that HDFS provides you, you would not have that. HBASE has bunch of APIs that include Java APIs, Gateway for REST, Thrift, and Avro. The master server that is responsible for managing the cluster, and the regional server manages the data. um, the client, if it wants the data, it needs to find out from the region server. So it's the region server which is holding on to the data. That within region server you have the file systems, which are the H files. You have the memory storage and the write ahead logs. We'll talk more about when we talk about the details around how data is written. The zookeeper is an important component and is a neural network. It bootstraps and coordinates a cluster, and without zookeeper there is no cluster. Uh, so the project will kind of explain the steps involved in installing the HBASE database, and we'll use the same CentOS based virtual machine that was used in the class for map reduced exercises, and that will make the entire process of installing HBASE simple, as it will use the same HDFS that was being used earlier. Um, in addition, it will use the Cloudera image and installs a pseudo distributed image, giving an introduction of various services that are involved as part of the HBase install. As part of the install, all the components like the master server, the region servers, and zookeepers are configured. Um, so, just a quick review. You to get started, you need to have the Hadoop installed. As part of that, you can actually download it from Cloudera CDH4. You can download the CentOS OS from mirrors.sees.harvard.edu/CentOS. You need to install the JDK 1.6.0_31 and set the Java home. Then you need to install the CDH tarballs as mentioned in our early exercise and install the Hadoop. Once you have done that, then you need to basically install the HBase, and we have used yum for that. So you can just do the sudo yum install HBase. Once you have that, you need to make sure that you basically have to change this property file. There's an HBase -site.xml, and this is required if you're actually doing a pseudo distributed mode. Once you've done that, you have to create a folder within the HDFS called /HBase, and then you can install the zookeeper server. If you're starting zookeeper for the very first time, you have to save zookeeper server in it, and then you can start the server, which is sudo service zookeeper server start, and then you start the master server and then the region server. I have already installed that in my VM, and I'm just gonna go ahead and just start the services to give an overview. So I'm gonna log in, and as part of that, I will starting with zookeeper, and once the zookeeper starts, I will start the master server, and after master server starts, I will start the region server. Once I have started all of it, I should be able to see this console with the right value. So I just refreshed it, so I was able to see that. And in addition to that, there is another command that you can use to find out what is the status of so let's go back to the PowerPoint again, and we'll see what command we're looking for. Saying sudo jps, and sudo jps, I should be able to get the list of all the services that are running. Right now I can see that it is region server, the master server, the quorum peer main, the JPS, they're all running. So it looks like we are in a good shape. And in addition to that, I can see the data node, the task trackers, and the name node, they're all running, which are required for HDFS. So we are in a good shape. Let's go back to the PowerPoint. So once we have installed this, we can actually go ahead and do some development using interactive mode. what you can do is you can launch this shell from your terminal using HBASE shell, and this shell provides you with tab completion of your command and inline access to command documentation. And so we could potentially just kind of quickly go over there and open the shell. And so the way you do it is you say HBASE shell, and you should see the shell now. So the shell has started. At this point I can list all my tables. I can create a table, so I can say create my test table, and when I create the table I need to define what's my column family. So I will just give a column family as CF1, and here I have a new table created. If you look at this code right now, it is trying to put an entry into an HBASE table, and in this scenario the row key is the first coordinate and followed by the column family. So when used as a data coordinate, the column family serves to group columns. So the next coordinate is a column qualifier. So this is the column family and it's grouping all the columns. So the column qualifiers in this scenario is the name and the email. And so because HBASE is a schemaless, you never need to predefine the column qualifier to assign them types. They're dynamic. So all you need is a name that you give them at right time. So these three coordinates define the location of a cell, and the cell is where HBASE stores data as a value. So a cell is defined by its row key, column family, and column qualifier. And so HBASE stores a piece of data based on four-dimensional system. So the coordinates used by HBASE in order are, as I mentioned before, row key, column family, column qualifier, and version. So version is something that is kind of unique in a sense that if you have multiple values or you have values that you have updated over time, you can actually keep the earlier versions as well, because time is also a coordinate there. So HBASE API is built such that you aren't required to provide the entire coordinate path when requesting the data. So let us discuss more on the internals of write within HBASE. So when you use put to record a new row in HBASE, the system basically receives a command, and it persists the change. So the way this works is that by default it goes into two places: the write ahead log, also referred as wall, right, and the mem store. So the mem store is a write buffer which HBASE accumulates data in memory before a permanent write. So its contents are flushed to form the H file when mem store gets filled up, right? So it does not write an existing H file, but instead forms a new file on every flush. So as you can see here, and the H file is the underlying storage format for the HBASE. So the thing is that H file always belongs to a column family, and a column family can have multiple H files, but a single H file cannot have data for multiple column families. How does it handle failures? So HBASE cluster keeps a write ahead log, right, to record changes as they happen. And so the wall or write ahead log is a file on the underlying file system, and a write is not considered successful until the new wall entry is successfully written. So this guarantee makes HBASE as durable as the file system back. Deleting the data is fairly straightforward. When you delete the data from HBASE, it does not get deleted immediately. It's essentially marked to be deleted, or a tombstone record is written. So only during compaction, the system takes over, the files are reconciled. And the way it works is that you make an instance with row key, you delete the entire row key, or you can delete only part of the row key by specifying the coordinates. This is the code. This is part of the submission. I have a driver class which basically would be in a position to do read, add, um, list, and you can run through that. It's fairly straightforward. This is the detail around that. As I said before, you essentially get the connection from the pool, and then you can do a put, you can add a user, you can do a scan of the user, you can get the user, you can delete a user using the APIs. Now, one of the things that we already talked about it, but I just want to reiterate, is that whenever you have two column families, the files are always separate. So that means that using separate H files for each column family means that HBASE doesn't need to read all the data for a row when performing a read. It needs to retrieve only data for the requested column family. So being column oriented means that HBASE need not read over placeholder entries when looking for a specific cell. So these physical details makes for a very efficient storage when looking for a specific cell. So let's say, right, you add another column family to the user table, or in this scenario, right, so you have two tables, two column families, info and activity here. You basically would always end up with multiple H files, and this allows basically to be able to grow without adversely affecting the performance, because each column family is basically using different file systems. And once you have that, then you can actually make sure that each column family again is persisted in different regions, and that way you exactly know where the data is hosted. At a high level, RDBMS is very structured and highly regular. Systems are optimized based on these standards. So HBASE is semi-structured, and so you got to make sure that and since it's semi-structured and the way the architecture is done, the logical and physical models are intermingled. So you need to have a very strong understanding for optimal use of a data system. The design is based on scale. HBASE uses coordinate system, as we talked about, right, to identify data. So HBASE is not ACID compliant database. The operations are row level atomic. Anytime you have a inter row operations, they would not be atomic. Scan across the table is not a snapshot of the table, so it does not guarantee that while you're doing a scan, if data changes, it does not guarantee that data would always be consistent. One of the things that we need to take a look at it, the way the data is structured, is that we talked about multiple H files per column family. So this is important on how to design column keys. As you can see here, right, on the left hand side, this is the logical representation of a table. So we have rows and we have columns. Then there are duplicate boxes where HBASE can carry time dimensions also. So now if you fold this, what happens is that then all columns basically go into one column, and then each column family would basically end up in a distinct file system. But if you look at it closely, the way the folding is happening is that you have all the column families of C1 and C2, they're becoming part of one column family file system, and then the second one is going there, and once it gets persisted into those H files, each of these values they basically can identify themselves. So while logical layout has no matching to physical layout, but when the values are stored, the row key, the column family, the column qualifier, and the timestamp, they're all part of the definition of that cell. So each of these guys can actually identify themselves, and that is how they can kind of scale out pretty easily, because each of these cells, they exactly know who they are. Um, so to finish the presentation, HBASE is a database. Um, it's a Hadoop database. It uses HDFS as its data store. It's sparse, distributed, persistent. It's multi-dimensional. Um, um, so HBASE is a database, Hadoop database. It is uh, it is designed for semi-structured data and horizontal scalability. It stores data in tables. Um, the data model is logically organized as key value store or as a sorted maps of maps. And HBASE is not a relational database, and tables are split into smaller chunks that are distributed across multiple servers via sharding. And region servers are basically used for that. Schema designs in HBASE are heavily influenced by anticipated data access patterns. So ideally, the tables in your schema are organized according to these patterns. The row key is the only fully indexed coordinate in HBASE, so queries are often implemented as row key scan. And compound row keys are a common practice in support of these scans. So an even distribution of row key value is often desirable. And hashing algorithms such as MD5 or SHA1 are commonly used to achieve even distribution. I think that's all I have. Thank you for listening.